In a lot of organic chemical reactions, the stereochemistry of the product is extremely important. You could generate a pair of enantiomers, which is basically a racemic mixture, or you could generate just one of the enantiomers, depending on the type of chemical reaction. In order to determine the stereochemistry of the product of an SN2 reaction, we have to look at how the nucleophile attacks the substrate. How does the nucleophile attack the electron-deficient carbon? So there are two possibilities in which a nucleophile can attack the electron-deficient carbon. The first possibility is via front-side attack, in which the nucleophile attacks the electron-deficient carbon on the same side as the leaving group. And then what you get is the retention of the structure. So essentially, the nucleophile replaces the bromine atom or the leaving group. And so the structure gets retained. The other possibility is a backside attack, in which the nucleophile attacks the electron-deficient carbon opposite the leaving group. And so what you have is an inversion of the structure. It's kind of like opening an umbrella. When you open an umbrella, it opens, but then it gets inverted. So that's basically a backside attack. You have an inversion of the structure. So as you can see here, the structures of A and B are actually similar, but their stereochemistry is different. The orientation of the bonds are different, right? The orientation of the bonds in space is different. And so when you put them in juxtaposition side by side, they're actually mirror images of one another. They're enantiomers. So here we have molecule A, which is the product of a front-side attack, in which its configuration is retained. And here we have molecule B, which is the product of a backside attack, in which the configuration is inverted. So what that means is that if the original substrate's configuration was an R configuration, then the configuration of molecule A would be the same as well. It would be R configuration. However, for the product of a backside attack, it would be inverted. So if the original substrate had an R configuration, then molecule B would have an S configuration. So as you can see, molecules A and B here are non-superimposable mirror images, which makes them enantiomers. All SN2 reactions proceed via backside attack. And so the result is an inversion of the configuration at the stereogenic center. So the product of an SN2 reaction will always be an inverted product, or it will have an inverted configuration, which makes a lot of sense, because if the nucleophile was to attack from the front, then it will actually interfere with the leaving group. Whereas if the nucleophile attacks from the back, then the leaving group can just easily detach from the electron-deficient carbon. So since an SN2 reaction is a concerted reaction, meaning it's bimolecular, it only has a single transition state. And in a transition state, you have a partially formed bond between the nucleophile and the electron-deficient carbon, and also a partially broken bond between the carbon and the leaving group. So the nucleophile will receive a partial negative charge, and then the leaving group will also receive a partial negative charge. So this is what the transition state looks like for SN2 reactions. So here are two examples showing you how a configuration gets inverted via SN2 reaction. So here we have a nucleophile that's attacking this electron-deficient carbon atom, and then notice that we have the leaving group that's drawn on the left-hand side. So that means that the nucleophile will be attacking from the right. And notice that these groups right here, the group of atoms, we have hydrogen, methyl, and ethyl groups that will get inverted as the sigma bond is formed between the nucleophile and the carbon atom, as shown here. So now we have the ethyl group that's drawn on the left, and then all the other ones are inverted as well. And the second example here, we have a hydroxide ion attacking the carbon atom. So notice that the chlorine atom, the leaving group, is drawn in front of the plane. And so that means that the nucleophile, the hydroxide ion, will be attacking opposite the leaving group, and so from the back. And so now this hydroxide ion forms a bond, a wedge, as a dash wedge, and then the hydrogen gets inverted and moves towards the front of the plane. So this is the inverted configuration for this product. So here's an example. Label the nucleophile and leaving group, and then draw the product, including stereochemistry, of the following SN2 reaction. So here we have a chemical reaction between 1-bromo-3-methyl cyclohexane and cyanide ion. So cyanide ion here is our nucleophile, and the bromine atom here is the leaving group. So notice here that the leaving group is drawn in front of the plane. And so that means that the nucleophile will be attacking from the back, right over here. And so the sigma bond that's formed between the nucleophile and the electron efficient carbon will be on a dashed wedge, which is shown here. So just letting you know that this carbon atom here has a hydrogen that's bonded to it on the dash wedge. And so now that gets inverted, which is now going to be on a normal wedge facing towards the front of the plane. And then the nucleophile is facing towards the back of the plane. So here's practice problem number 20. Draw the product of each SN2 reaction and indicate the stereochemistry. So here on the right hand side we have the nucleophile, and then on the left we have the alkyl bromide. So you can see that this carbon atom right here is a stereogenic center because of the fact that it contains 4 different groups of atoms. The D here is deuterium, which is one of the isotopes of hydrogen. And so since the bromine atom, the leaving group, is drawn on the right hand side, the nucleophile will be attacking from the left, as shown here. And so the bromine atom detaches from the carbon atom, and the bond between the carbon and the oxygen will form. And then so these 3 groups of atoms right here, the deuterium, ethyl group, and the hydrogen, will now be inverted, meaning they will be facing towards the right hand side, as shown here. So here you can see that the deuterium, the ethyl group, and the hydrogen are now drawn facing towards the right hand side, opposite of the original configuration. And for the second reaction here, we have the cyanide ion as the nucleophile, and then we have the iodine atom, which is oriented towards the front of the plane. So that means that this nucleophile will be attacking this electron deficient carbon atom from the back. And so then this iodine detaches from the carbon atom, and now the cyanide ion will form a sigma bond oriented towards the back of the molecule. And so we have this cyclohexane ring, or cyclopentane ring, and then we have the cyanide ion, or the cyanide group, bonded to this carbon atom facing towards the back of the plane. The type of carbon atom that's bonded to the leaving group can actually affect the rate of an SN2 reaction. As the number of R groups on the carbon with the leaving group increases, the rate of an SN2 reaction decreases. So for example, the rate of an SN2 reaction for a primary carbon is a lot higher compared to a secondary or a tertiary carbon. And the main reason behind this is because of the crowdedness or the bulkiness of the molecule. A tertiary carbon is bulkier compared to a secondary or a primary carbon. And since primary carbons are not as bulky compared to a secondary or tertiary carbon atoms, nucleophiles can attack this electron deficient carbon atom a lot easier, which results in the increase in the rate of reaction. And so because of this, methyl and primary alkyl halides undergo SN2 reactions pretty easily. Secondary alkyl halides react a little bit more slowly, and tertiary alkyl halides do not undergo SN2 reactions at all due to steric hindrance. And the bulky R groups near the reaction site make nucleophilic attack from the backside a lot more difficult, which slows down the reaction rate. So here we have the electron distribution maps for 4 different molecules, showing you how much more difficult it is for a nucleophile to attack a bulkier molecule and how that affects the reactivity. So from left to right, we have methyl bromide, ethyl bromide, isopropyl bromide, and tert-butyl bromide. So as you can see, the tert-butyl bromide is the bulkiest in this group. And so we have increasing its steric hindrance from left to right, and the reactivity increases from right to left, in which the methyl bromide is the most reactive via SN2 reaction. So here's a table that summarizes the characteristics of an SN2 reaction mechanism. So an SN2 reaction has second order kinetics, which means that the reaction rate is dependent upon both the concentration of the nucleophile and the alkyl halide. The SN2 reaction mechanism happens in a concerted reaction, meaning it happens in a single step. And the backside attack of the nucleophile results in the inversion of the configuration at the stereogenic center. And finally, unhindered halides react much faster compared to bulkier halides. So here's practice problem number 21. Which compound in each pair undergoes a faster SN2 reaction? So for the first pair right here, the first thing that we want to do is to identify the classification of the alkyl halide. Do we have a primary, secondary, or tertiary alkyl halide? So the first one here is a secondary alkyl halide. And the second one here is a primary alkyl halide. So according to the characteristics of an SN2 reaction, primary halides will react much faster compared to secondary halides. And for the second problem here, we have a secondary halide here and a tertiary halide. And so in that case, the secondary halide will react much faster via SN2 reaction. So here's another example of an SN2 reaction. Identify C, the product of an SN2 reaction in the synthesis of raloxifene, a drug used to reduce the risk of invasive breast cancer. So we have 2 molecules here labeled A and B, and they're reacting with each other via SN2 reaction. So we have to identify which one is a nucleophile and which one is the alkyl halide. So as you can see, this molecule B here has a halogen. So this is going to be the alkyl halide. So that must mean that molecule A is our nucleophile. But first we have to activate this nucleophile. So one way to do that is to use this potassium carbonate to activate this this oxygen right here, which will be our nucleophilic atom. All right, so how does that work? So we have the molecule. So we have CO3 with a -2 charge, and so this will deprotonate this alcohol, and then the lone pair of electrons will transfer towards the oxygen. So now we have a negatively charged oxygen here. So here's the product of the first chemical reaction, the activation of the nucleophile. So now we have HCO3 with a negative charge, a bicarbonate, and our nucleophile right here. So this nucleophile will attack the alkyl halide. And so this carbon right here is the electron deficient carbon. And the nucleophile will attack this carbon, which results in the cleavage of this bond, and then the lone pair of electrons will be transferred towards the more electronegative chlorine atom. And so now we have this product that's shown here. So notice that this carbon atom is not a stereogenic center, and so you don't have to worry about the stereochemistry around this carbon atom. So this is the product of this chemical reaction equation. So we're going to go ahead and switch gears here and talk about Sn1 reaction mechanism, which is of course different from Sn2 reaction mechanism. It involves two steps. The first step is a slow step, which is also known as the rate determining step. This is a slow process because it involves the heterolysis of the sigma bond between the carbon and the halogen. And this generates a reactive intermediate, which is a carbocation, a carbon with a positive charge. Now, the second step involves the reaction between the nucleophile and the carbocation, which results in formation of a new bond, a new sigma bond, between the nucleophile and the positively charged carbon. So that's the mechanism for an Sn1 reaction, and make sure that you know how to differentiate an Sn2 from an Sn1 reaction. And here are some of the known facts regarding Sn1 kinetics that you've already learned in a previous lesson. So Sn1 reactions, again, exhibit first-order kinetics because they are unimolecular, which means that the reaction rate is only affected by the concentration of the alkyl halide and not the concentration of the nucleophile. So again, the nucleophile does not have any effect on the reaction rate, and so it does not appear anywhere in the rate law equation. So here's an example of an energy diagram for an Sn1 reaction. Again, Sn1 reactions involve two steps, which means that it's going to have two transition states and two activation energies. So the first step is the rate determining step, and so the activation energy is greater compared to the second activation energy. This is the transition state for the first step, which involves the cleavage of the sigma bond between the electron deficient carbon and the halogen. And this results in formation of a reactive intermediate, which is a carbocation. And then the second step involves the reaction of the carbocation with the nucleophile, which again results in the formation of the sigma bond between the nucleophile and the carbon atom. And then the energy decreases as the products are formed. So the stereochemistry of Sn1 reaction is different from Sn2 reactions, and here's why. So when you look at the reactive intermediate, which is the carbocation that's generated from the rate determining step, you can see that this carbon here is sp2 hybridized, which makes this carbocation a trigonal planar. So it's a flat molecule, or it's a flat carbocation. And so that means that when this undergoes reaction on the second step with the nucleophile can attack this carbocation on both sides of the plane, because this carbocation has a vacant p orbital that's protruding above and below the plane. And so again, the nucleophile can attack this carbocation on either side of the plane. So this suggests that the nucleophile can attack this electron deficient carbon via a front side attack or a back side attack. And as you learned from the Sn2 reactions, that depending on where the nucleophile attacks will generate a different kind of molecule. And so for Sn1 reactions, you will get two different kinds of molecules with equal concentration. And so again, Sn1 reactions involve two steps. The first step is the rate determining step, and this is a slow step. It's a slow process. And the sigma bond between the bromine atom and the electron deficient carbon gets cleaved, and this results in the formation of a reactive intermediate. They call this carbocation. And this carbocation has a trigonal planar geometry, which makes it a flat molecule. And this allows the nucleophile to attack this electron deficient carbon on either side of the plane. So it can attack this carbon via front side attack or back side attack. And depending on which side the nucleophile attacks, it will generate a different molecule. So for example, if the nucleophile attacks from the front, then you get this configuration. So if this was a stereogenic carbon, then we have an enantiomer. And so if the nucleophile attacks from the back, then it will also generate a different configuration. So notice that in B, you have the nucleophile that's facing towards the front, and then the molecule, the product of the backside attack, the nucleophile is facing towards the back. And so as you can see here, B and C are enantiomers of one another. We have a pair of enantiomers here. And so the nucleophile will attack this carbocation on either side of the plane with equal probability. And so we will have 50% of B and 50% of C. So they call this racemization because we get equal amounts of the enantiomers. We get a racemic mixture. So again, you get racemization in Sn1 reactions as long as this carbon here is a stereogenic center. So you know that this is a stereogenic center because this carbon is connected to 4 different groups, right? So this carbon is different from this carbon because this carbon here is connected to a deuterium, which is a different isotope of hydrogen. And so it makes this carbon a chiral carbon or a stereogenic center. So that's the main difference, the main differences between Sn1 reactions and Sn2 reactions. So here are 2 examples of racemization in the Sn1 reaction. So again, the very first step in Sn1 reaction is the generation of the carbocation. So this sigma bond right here between the iodine and the carbon atom will be cleaved, and that generates a carbocation, which is the reactive intermediate. And then the nucleophile will attack that carbocation on either side of the plane. And so it will generate 2 enantiomers. They are non-superimposable mirror images. And so in that case, we have a racemic mixture. And here's another example here. We have a chloride or a chlorine atom, and this is attached to a chiral center. And you know that this is a chiral center or a stereogenic center because this carbon is connected to 4 different groups. We have 1, 2, 3, and 4. And so again, the first step generates the carbocation, and then this nucleophile will attack on both sides of the carbocation and will generate a racemic mixture. So here's practice problem number 24. Draw the products of each Sn1 reaction and indicate the stereochemistry of any stereogenic centers. So here we have a reaction between 3-bromo-2,3-dimethylpentane with water, and water is the source of nucleophile here. And since this is undergoing Sn1 reaction, we will get a racemic mixture, a mixture of 2 enantiomers, a pair of enantiomers. And so if the nucleophile attacks via the front, then the nucleophile basically replaces this leaving group, which is the bromine atom. And if the nucleophile attacks from the back, then it will be oriented differently. And so instead of protruding from the back, it will be facing towards the front. So let's draw the products of this Sn1 reaction. So for the first reaction here, we have these 2 organic products, which are non-mirror or non-superimposable mirror images. So they are a pair of enantiomers. And this inorganic acid right here is the byproduct. So for the second one here, we have 1-chloro-4-ethyl-1-methylcyclohexane. And then we have a nucleophile here, which is the acetate ion, and this acetate ion will attack this electron deficient carbon atom right here. And so let's take a look at the 2 possible products for this Sn1 reaction. So here are the 2 products, 2 organic products of this Sn1 reaction, and then chloride ion is a byproduct. And so as you can see, when this nucleophile, this acetate ion, attacks from the front, then it basically just replaces this chlorine atom. And so what the product that we get is this first one right here, in which the acetate ion just replaces the chloride atom. And so if the nucleophile, the acetate ion, attacks from the backside attack, then this is the configuration that we will get. So there's an inversion of the configuration. So when you compare these 2 molecules here, these 2 organic products, they're actually not mirror images. They're not even mirror images. And so that means that these 2 products are actually diastereomers of one another and not enantiomers. So earlier we looked at how the type of alkyl halide affects the rate of an SN2 reaction. We determined that tertiary alkyl halides are bulkier compared to secondary or primary or methyl halides, and so it's a lot more difficult for the nucleophile to attack that electron deficient carbon in a tertiary alkyl halide. And so in terms of reaction rates of an SN2 reaction, methyl halides and primary halides have a much faster reaction rate compared to secondary or tertiary. Again, because that nucleophile can access that electron deficient carbon a lot better. So here we're going to do the exact same thing and take a look at how the type of alkyl halide affects the rate of an SN1 reaction. And so for SN1 reactions, as the number of R groups on the carbon with the leaving group increases, the rate of the SN1 reaction also increases. So that means that a tertiary alkyl halide actually reacts a lot faster compared to a secondary, primary, or a methyl halide. And so this trend is the exact opposite to that observed in SN2 reactions. And the reason behind this is because of the carbocation, the stability of the carbocation that's generated during the rate determining step. And we're going to take a look at the stability of these different types of carbocations in the next few slides. So here's a table that summarizes the different characteristics of the SN1 mechanism, which is the complete opposite of the SN2 reaction. So an SN1 mechanism has first order kinetics, so that means that the reaction rate is only dependent upon the concentration of the alkyl halide and not the concentration of the nucleophile. And so this also tells us that this is a unimolecular reaction. The mechanism involves two steps. The first is the rate determining step, and then the second step is a fast step. And the carbocation that's generated during the rate determining step is trigonal planar in geometry. So that means that the nucleophile can attack the carbocation on either side of the plane. And in terms of stereochemistry, because of the nature of the carbocation, we can get racemate, which is a mixture of enantiomers, if the alkyl halide is or contains a stereogenic center. And in terms of the reactivity of the alkyl halide, the more substituted halides are, the faster they react. And so if you have tertiary versus secondary versus primary, the reaction rate increases as the alkyl halide becomes more substituted. So the reaction rates observed in SN1 reactions can be explained by looking at the stability of the carbocations. So carbocations can be classified as primary, secondary, or tertiary depending on the number of carbons bonded to the electron deficient carbon atom. And so you can see over here that as the number of R groups, or the number of carbon atoms bonded to that electron deficient carbon increases, the carbocation stability also increases. So that tells us that tertiary carbocations are the most stable, whereas methyl carbocations are the least stable. And there are two theories explaining the stability of these carbocations. So here's practice problem number 25. Classify each carbocation as primary, secondary, or tertiary. So for the first carbocation here, you can see that this carbon atom is only bonded to two carbon atoms. So that means that we have a secondary carbocation here. For the second example, we have this carbon right here, which is bonded to one other carbon atom. So that means that we have a primary carbocation here. And for the third example, this carbon right here is bonded to 1, 2, 3 other carbon atoms. And so that means we have a tertiary carbocation. And the last one is this carbon right here bonded to two other carbon atoms. So we have a secondary carbocation. So there are two theories that can explain the stability of the carbocations. One is via inductive effects, and the other one is via hyperconjugation. So in one of the previous chapters, we've looked at inductive effects and used it to explain the relative strengths of acids. And so we can use this theory to explain the stability of carbocations as well. So again, inductive effects occur by the pull of electron density through sigma bonds caused by the electronegativity differences between atoms. So alkyl groups, which contain carbons, are not very electronegative. They're actually electropositive. And so instead of pulling the electrons towards themselves, they're more donating, right? They donate electrons. And so that helps stabilize a positive charge. Because again, a carbocation is electron deficient, so it wants some electrons. And so these alkyl groups containing a bunch of carbon atoms, they're able to donate electrons and stabilize that positive charge. Another reason is because alkyl groups are more polarizable than a hydrogen atom, and so they are able to donate electron density a little bit better compared to hydrogen atoms. So in that case, the more alkyl groups you have, or the more carbon atoms you have attached to that electron deficient carbon atom, the more stable the carbocation will be. And the second theory here that explains the stability of the carbocations is hyperconjugation. And by definition, hyperconjugation is the spreading out of charge by the overlap of an empty p orbital with an adjacent sigma bond. So here we have two examples. We have a methyl carbocation and a secondary carbocation. So you can see that in the methyl carbocation, there's no hyperconjugation because we don't have an adjacent sigma bond here. On the other hand, for the secondary carbocation, we have several adjacent sigma bonds. We have the sigma bonds here present on an adjacent carbon. Same thing on this adjacent carbon here. We have several sigma bonds. And so they help in stabilizing this positive charge on the carbocation. Since the stability of carbocations is very important in Sn1 reactions, this brings us to the Hammond postulate. And the Hammond postulate basically relates the reaction rate to stability. And then we're going to go back to kinetics and look at energy diagrams, activation energies, transition states, because the Hammond postulate provides a quantitative estimate of the energy of a transition state. And this also states that the transition state of a reaction resembles the structure of the species to which it is closer in energy. So the Hammond postulate basically summarizes what we just talked about regarding the stability of carbocations and how that relates to the rate of Sn1 reaction. So the rate of Sn1 reaction increases with increasing carbocation stability. So the more stable the carbocation is, the faster the rate of Sn1 reaction. So you can see here that a tertiary carbocation is more stable compared to a secondary, a primary, or a methyl. And so that means that a tertiary carbocation undergoes Sn1 reaction at a much faster rate. And so again, the rate of the Sn1 reaction increases with increasing carbocation stability. So according to the Hammond postulate, the structure of the transition state resembles the structure of the species that's closer in energy to the transition state. So here we have two examples, one for an endothermic reaction and one for an exothermic reaction. For an endothermic reaction, you can see here that the transition state is closer in energy to the products than it is to the reactants. So this suggests, according to the Hammond postulate, that the structure of the transition state resembles the structure of the products more than the reactants. And here you can see for an exothermic reaction that the transition state is closer in energy to the reactants than it is to the products. So again, according to the Hammond postulate, the structure of the transition state resembles the structure of the reactants more than the products. And since the transition state resembles the products more in an endothermic reaction, anything that stabilizes the product will also stabilize the transition state. So what does it mean by stabilizing the product? So that means that if we were to decrease the energy of the product, will also result in a decrease of the energy of the transition state. And if we were to decrease the energy of the transition state, that means we're decreasing the activation energy, which ultimately increases the reaction rate. And for an exothermic reaction, you can see that the transition state resembles the reactants more. And so decreasing the energy of the products actually has little effect on the energy of the transition state, because the transition state is closer in energy to the reactants. And so activation energy is not affected, and so the reaction rate is not affected either. So here's a side-by-side comparison between an endothermic reaction and exothermic reaction, and how lowering the energy of the products will affect the energy of the transition state and ultimately the reaction rate. So again, for an endothermic reaction, if we were to stabilize the energy of the products by lowering the energy of the products, will result in the decrease in the energy of the transition state and also the activation energy, which ultimately increases the rate of reaction. And for an exothermic reaction, stabilizing the products or lowering the energy of the products won't really affect the activation energy, because again, the energy of the transition state resembles that of the reactants, or closer to the energy of the reactants. And so the reaction rate won't be affected by stabilizing the energy of the products. So in an SN1 reaction, the first step is actually an endothermic process. So that rate determining step, the slow step, is an endothermic process. Energy has to come in order to form that carbocation. And so that carbocation is basically the product of that first step. So if we can stabilize that product, then we can decrease the activation energy, and in turn increases the reaction rate. And so a more stable carbocation results in a much faster reaction rate. So here we have a direct comparison between a tertiary carbocation and a secondary carbocation. So you can see that the tertiary carbocation is more stable because it's lower in energy than the secondary carbocation. In addition, the transition state of the secondary carbocation is higher in energy than the transition state of the tertiary carbocation. And so that means that their activation energies are also different, in which the activation energy of the less stable carbocation is greater than the activation energy of the more stable carbocation. And so therefore, the more stable carbocation, the tertiary carbocation, will react much faster compared to the secondary carbocation. So here's practice problem number 27. Which alkyl halide in each pair reacts faster in an SN1 reaction? So the first thing that you should do here is to classify the carbon atom that's bonded directly to the halogen. And so we have the halogens here, so we're going to go ahead and circle them. And the halogen is bonded to this carbon atom. And so this carbon is classified as a tertiary carbon atom because it's bonded to 3 other carbon atoms. And for the second one here on the right, this carbon is bonded to 1 other carbon atom. So that must mean that this is a primary carbon. And so the carbocation that's generated will be tertiary for this one, and then primary for this second alkyl halide. And so we know that tertiary carbocations are more stable than primary carbocations. So in that case, this alkyl halide will react much faster compared to this alkyl halide. And for the second pair here, we have a tertiary carbon and a secondary carbon. And so again, a tertiary carbocation is more stable than a secondary carbocation, and therefore this alkyl halide will react much faster than the second one. So now that you know more about SN1 and SN2 reactions, how do we know whether a nucleophilic substitution reaction will undergo SN1 or SN2 mechanism? So now we're going to put everything together and look at these 4 factors that will allow us to predict the mechanism of the nucleophilic substitution reactions. Is it going to be an SN1 reaction or is it going to be an SN2 reaction? So depending on these 4 factors and the combination of these factors, you could either have an SN1 or an SN2 reaction. As you have learned earlier, the type of alkyl halide is very, very important because it generates a specific type of carbocation. You can have a stable carbocation or an unstable carbocation. So again, you can generate a methyl carbocation, a primary, secondary, tertiary, depending on the type of alkyl halide that you have. The nucleophile, the strength of the nucleophile can also affect the mechanism of the nucleophilic substitution reaction. The type of leaving group. Do you have a poor leaving group or a good leaving group? The type of solvent can also affect the mechanism of the nucleophilic substitution reaction. Do you have a protic solvent or an aprotic solvent? The most important factor that affects the mechanism of a substitution reaction is the identity of the alkyl halide. Do you have a methyl halide, primary halide, secondary, or tertiary halide? So you learned that the rate of an SN1 reaction increases as the stability of the carbocation increases. So that means that a tertiary alkyl halide will undergo SN1 reaction the fastest compared to secondary, primary, or methyl halide. On the other hand, for an SN2 reaction, you want the alkyl halide to be less bulky and more open to a backside attack by the nucleophile. So that means that methyl halides and primary halides will undergo SN2 reaction much faster compared to a secondary or a tertiary alkyl halides. And for secondary alkyl halides, they can undergo both SN1 and SN2. So you would have to look at other factors that will lead them to the specific mechanism. So here's practice problem number 28. What is the likely mechanism of nucleophilic substitution for each alkyl halide? So in order to determine this, we're going to have to look at the identity of the alkyl halide. So for the first one here, we have this halogen right here, which is connected to this carbon atom, and this carbon is a secondary carbon atom. And so this could either go SN1 or SN2. And for the second alkyl halide here, again, we have a bromine atom, which is our halogen, and it's bonded to this carbon atom right here. And this carbon atom is bonded to one other carbon atom. So we have a primary alkyl halide here. And so because this is a primary alkyl halide, it will undergo SN2 reaction. And for the third one here, we have bromocyclopentane, and you can see that this carbon atom that's directly bonded to the bromine atom is a secondary carbon. And so we have a secondary alkyl halide. So in that case, this molecule or alkyl halide can undergo either SN1 or SN2 reaction. And for the fourth one, we have 2-bromo, 2-methyl butane. So you can see that this alkyl halide is going to be a tertiary halide. And so we have an alkyl halide that will undergo SN1 reaction. The strength of the nucleophile can also affect the type of substitution reaction. Strong nucleophiles favor SN2 reactions, whereas weak nucleophiles favor SN1 reactions. Strong nucleophiles typically bear a negative charge, such as hydroxides and alkoxides, whereas weak nucleophiles are neutral, like water and alcohols. So let's take a look at this one scenario here and see what happens to this molecule cis-1 bromo-4 methyl cyclohexane if we were to react this with a strong nucleophile such as a hydroxide versus a weak nucleophile such as water. Since strong nucleophiles favor SN2 reactions, we know that this reaction between this molecule and hydroxide will undergo SN2 reaction. So that means that this reaction right here will happen in a single step without the formation of a carbocation. This also means that the sigma bond that's formed between the nucleophile and the carbon atom will form at the same time as the sigma bond between the carbon and the bromine atom breaks. And finally, since this nucleophile approaches this molecule via backside attack, there's going to be an inversion of configuration. And so again, this undergoes SN2 reaction. And because we have an SN2 reaction, there's going to be a backside attack and inversion of configuration. So we have cyclohexane here. We have a methyl group right here. And then, so that means that the hydroxy group or the alcohol group will have a dash wedge. So we know that this is facing towards the back. And then, of course, our leaving group, which is the bromide ion. And if we're using a weak nucleophile like water, then it's going to undergo Sy1 reaction. And so the first step is the rate determining step, which is the formation of a carbocation right here. And then the water, which is acting as a nucleophile, can attack this carbocation on either side of the plane. And because of that, we're going to have a mixture of two different products with different configurations. If the nucleophile attacks from above, then we're going to have a cis isomer. However, if the nucleophile attacks from below, then we're going to have a trans isomer. And because we have a bromide ion that's generated, this bromide ion is acting as a base, which will then deprotonate one of these hydrogens here, which results in the formation of an alcohol. So here are the products of this Sy1 reaction. As you can see, we have a mixture of diastereomers. We have a cis isomer and a trans isomer. Here's practice problem number 29. For each alkyl halide and nucleophile, draw the product of nucleophilic substitution. And then for the second part here, determine the likely mechanism, Sn1 or Sn2, for each reaction. So let's take a look at this first one here, this first reaction. So the first thing that I would want to do here is to identify the classification of the alkyl halide and then the strength of the nucleophile. So you can see that the alkyl halide here is a tertiary alkyl halide because this carbon atom is bonded to 3 other carbon atoms. So we have a tertiary alkyl halide, and then for this nucleophile right here, you can see that it is neutral. There's no negative charge anywhere, and so this is going to be a weak nucleophile. And we know that tertiary alkyl halides are more likely to undergo Sy1 reaction because of the fact that it generates a tertiary carbocation, which is a stable carbocation. And so in that case, we have an Sy1 reaction. So again, the alcohol or the nucleophile will attack the carbocation that's generated from the rate determining step, which then results in the formation of this positively charged product right here with the oxygen with a positive charge. And because this reaction also generates a chloride ion, this chloride ion will act as a base, which will then deprotonate this hydrogen right here. And so because of that, we will have an ether. So the product of this reaction will be a molecule containing an ether functional group. And of course, plus the hydrochloric acid. And that's it. And for the second reaction here, you can see that this alkyl halide right here is a primary alkyl halide because this carbon that's bonded directly to this halogen is bonded to one other carbon atom. And so what we have here is a primary alkyl halide. And this nucleophile here has a negative charge. So we know that this is going to be a strong nucleophile. And so in that case, because we have a primary alkyl halide and a strong nucleophile, this reaction will most likely undergo Sn2 reaction because we want that carbon, electron deficient carbon, to be open and not very bulky. And so we can have a backside attack coming from the nucleophile. And so the sigma bond between the nucleophile and the primary carbon over here will form, and then so this nucleophile right here will attack this electron deficient carbon atom, which will form a sigma bond, and at the same time the sigma bond between the carbon atom and the leaving group will break. And so now what we have are the two products of this chemical reaction. So again, this is an Sn2 reaction, and so we have a bromide ion, which is also one of the byproducts. So for the third reaction here, you can see that we have a secondary alkyl halide. And the nucleophile is considered a strong nucleophile because it has a negative charge. And so in that case, this reaction can go either SN1 or SN2 reaction. And so because SN1 and SN2 reactions are both possible, then these are the products that will form for this chemical reaction. And finally, for this fourth chemical reaction here, you can see that this alkyl halide is also a secondary alkyl halide. And you can see that we have methanol here acting as a nucleophile. So this is considered a weak nucleophile because of the fact that it's a neutral molecule. And since we have a secondary alkyl halide here, this reaction can undergo either SN1 or SN2 reaction. And because we're using a weak nucleophile here, then this chemical reaction will most likely favor SN1 reaction. So the third factor that affects substitution reactions is the nature of the leaving group. A better leaving group increases the rate of both SN1 and SN2 reactions. And you always have to remember that the weaker the base, the better the leaving group. And the last factor that affects substitution reactions is the type of solvent used. Polar protic solvents favor SN1 reactions because the ionic intermediates, such as the carbocations, are stabilized by solvation. On the other hand, polar aprotic solvents favor SN2 reactions because nucleophiles are not very well solvated, which makes them a lot more nucleophilic. Here's practice problem number 32. Which solvents favor SN1 reactions and which favor SN2 reactions? So in order to answer this question, you have to remember that polar protic solvents favor SN1 reactions. And polar aprotic solvents favor SN2 reactions. And so now we have to determine whether we have a protic solvent or an aprotic solvent. So if we have solvents that are capable of hydrogen bonding, then that means we have polar protic solvents. Whereas those that are incapable of hydrogen bonding, then they are polar aprotic solvents. So here we have a polar protic solvent. And so that means that this will favor SN1 reactions. And for the next solvent right here, this is acetonitrile, CH3CN. And you can see that this is incapable of hydrogen bonding with itself. And so this is considered aprotic. And this will favor SN2 reactions. And the third part here, this one is capable of hydrogen bonding. So this is a protic solvent, and so this will favor SN1 reaction. And finally, the fourth one here, this is aprotic, and so it will favor SN2 reaction. And here's another practice problem. Decide on the mechanism for each substitution, and then pick the solvent that affords the faster reaction. And so for the first reaction here, we have a tertiary carbon. So this halide right here is a tertiary alkyl halide because this carbon is connected to two carbon atoms and another carbon right here. So it makes this a tertiary carbon. And when you look at the nucleophile here, this is an alcohol. This is neutral. So it makes this nucleophile weak. And so in that case, since we have a tertiary alkyl halide, most likely this is going to undergo SN1 reaction because a tertiary carbocation is considered a stable cation, and so we would want a protic solvent to use for this reaction. And so we have CH3OH, which is protic solvent, and protic solvents favor SN1 reactions, and so we would choose methanol here. And for the second reaction here, you can see that this alkyl halide here is a primary alkyl halide because this bromine atom is bonded to this carbon atom, and the carbon atom is bonded to one other carbon, which makes this a primary alkyl halide. And primary alkyl halides are most likely going to undergo SN2 reaction. And you can see that the hydroxide group is a strong nucleophile. And so because this is going or undergoing SN2 reaction, we want the nucleophile to be not very well solvated so that it can attack the primary carbon, which is the electron deficient carbon. And so we would want DMF, dimethylformamide, to be the solvent used here because this is an aprotic solvent. And for the third part here, you can see that this alkyl halide here is a secondary halide because this carbon that's directly bonded to the chlorine atom is bonded to two other carbon atoms. And so that means that this reaction could undergo SN1 or SN2 reaction. But when you look at the nucleophile, we have a strong nucleophile here. We have a negative charge, and this is a methoxide ion. So this is a strong nucleophile. And since we have a strong nucleophile, this is most likely going to undergo SN2 reaction because strong nucleophiles favor SN2 reactions. And since we have an SN2 reaction, it's a lot better to use an aprotic solvent because aprotic solvents favor SN2 reactions. So methanol here is protic solvent, whereas HMPA is an aprotic solvent. So this is the one that we want. So here's a table that basically summarizes the different factors that determine whether you're going to have an SN1 or an SN2 mechanism. So make sure that you remember all of these. I think this is a very important table that will definitely help you in differentiating SN1 from an SN2 reaction. So again, the main factor that affects the mechanism is the type of alkyl halide. So if you have a primary alkyl halide, most likely this will undergo SN2 mechanism. If you have a tertiary alkyl halide, then you have an SN1 mechanism. However, if you have a secondary alkyl halide, it can either go SN1 or SN2. And so if you wanted to go SN1 reaction, then you would have to look at the type of nucleophile. So if you use a weak nucleophile, then most likely it will favor SN1 reaction. But if you use a strong nucleophile, then it will favor SN2 reactions. And then you're going to start looking at solvents as well, because there are solvent effects. So if you use protic solvents, then that will favor SN1 reactions, whereas aprotic solvents will favor SN2 reactions. And here's another practice problem. Determine the mechanism of nucleophilic substitution for each reaction and draw the products. So for the first reaction here, we have a primary alkyl halide reacting with a strong nucleophile. So we have primary and a strong nucleophile. So because of this, this reaction will favor SN2 reaction. And so that means that we're going to have a backside attack. So the nucleophile will attack this electron deficient carbon atom, and then the lone pair will transfer towards the bromine atom, and what we have is this product right here. And for the second reaction here, we have a secondary alkyl halide and a strong nucleophile. So a secondary alkyl halide can either go SN1 or SN2, but because we're using a strong nucleophile here, this is going to favor SN2 reaction. And so again, the nucleophile will attack this electron deficient carbon atom, and then the lone pair will go towards the bromine atom. And so what we have here is this organic product plus bromide ion as the leaving group. Here's another example. Determine the mechanism of nucleophilic substitution for each reaction and draw the products including stereochemistry. When you look at this first reaction here, you can see that we have a secondary alkyl halide, because again, this carbon atom right here is connected to two other carbon atoms. So we have a secondary alkyl halide, and then we have a strong nucleophile. This is a strong nucleophile because we have a negative charge, and this is a methoxide ion. And so this will favor SN2 reaction. And so that means that we're going to have a backside attack, and there's going to be an inversion of the configuration. And so what we have here will be CH3 and then the oxygen bonded to this carbon atom. And then we have the methyl group right here, CH3. And then the hydrogen. And finally, the ethyl group. Alright, and of course the chloride ion. And for the second reaction, we have a tertiary alkyl halide because this carbon atom is bonded to three other carbon atoms. And so we have a tertiary alkyl halide here. And you can see that we have a neutral alcohol, and this is a weak nucleophile. And so in that case, this is going to undergo SN1 reaction. And so that means that we're going to have a mixture of products. And so we have this alcohol, this nucleophile that will attack via either the front side attack or a backside attack. And so we're going to have two different isomers here. And the first isomer will have the same configuration as the original alkyl halide. And the other isomer would have the opposite. And here's one last practice problem. Determine the mechanism and draw the products of each reaction. Include the stereochemistry at all stereogenic centers. So for the first reaction here, you can see that we have a primary alkyl halide and a strong nucleophile. And so in that case, this chemical reaction right here will undergo SN2 reaction. And so there's going to be a backside attack. And so the product will be this. And for the second reaction, you can see that we have a secondary alkyl halide here and a strong nucleophile. And again, this reaction will favor SN2 reaction. And so the product is going to be, again, this is a backside attack. And since this is the stereogenic center, there's going to be an inversion here. And for part C, we have a tertiary alkyl halide. And this is a weak nucleophile. And so this is going to favor SN1 reaction. And so this will attack the electron deficient carbon atom, forming a tertiary carbocation. So what we have here will be this product right here. And since we don't have a stereogenic center, the only type of organic compound or organic product will be this right here, shown here. And for the final reaction here, you can see that we have a tertiary alkyl halide and a weak nucleophile. And so in that case, we're going to have an SN1 reaction. And you can see that this is a stereogenic center, and so we're going to have a mixture of products. So the first one will have the same configuration as the alkyl halide. And then the second one will be the opposite.